All right, so we are together. So we have recently had one of the biggest statistical events, and I'll be using that to bring in these concepts of statistics to our understanding, and that is the electoral process or the elections that we conclude. Okay, the presidential elections particularly. So before I start, I would like to say that I'll be quoting figures for strictly study purpose. I will sometimes mention inaccurate or approximate data. I hope you do not focus on the politics, but instead seek to see that these concepts are well understood by you. So to start with, population versus sample. So population in the context of the election, a good example would be the national election, whereby everyone was required to vote. Then a sample would be the primaries, the NRM primaries. Those who were following them, you'd find that delegates are selected from every sub-county and they are flown to Kololo and then they vote on behalf of the whole population in their area. And that's how they come up with posts like national vice chairperson and the rest. So if we go ahead and look at variable types, categorically, you will think of like maybe the district preference. You will find that there are districts that were preferring NRM, there are districts that were preferring NUP, and the rest. So those that would be categorical data. If you to have a map and some areas are blue and the others are red, depending on the voter preference, who took the majority votes, then that would be an example of categorical data. When we go ahead and look at numerical, which is divided into discrete and continuous, starting with discrete numerical, you talk about the number of votes per party. For example, NRM versus NUP. If you were to count the actual votes, that is discrete numerical data because we cannot have half vote, a quarter vote, 0.01 vote. So it is they all discrete data comes as a result of counting. Then continuous data comes as a result of measurement. Maybe an example would be the percentage. Think of the percentage voter turnout in different areas. For example, Kampala was about 44%. Soroti this side was about 50%. Then places like Bukedia had about 94%. So these percentages, actually, if you were to look at the data, it would be like 44.6%, 50.1%, then 54.7%. This way, you realize that this is the decimal points. That means this is what? Continuous data, continuous. Discrete as a result of counting, continuous as usually as a result of measurement or calculation. That's why we end up with decimal points and fractions. So going ahead to levels of measurement, still using the example of the election because we all saw the process and we're all following it. We look at nominal, ordinal, interval, and ratio. So starting with nominal, we can look at the names of district and a nominal district names. That is nominal data. It's not related. One district can be called Soroti, one district can be called Ginger, and going forward like that. If you look at ordinal, here we look at ordered lists. For example, if we were to rank the voter turnout per region, if we were to rank the regions by voter turnout, what we would end up with is ordinal data. For example, if we say maybe number one, the regions maybe we have Western, we have Central, we have Eastern, we have Northern, and which one am I missing? Okay, if we look at this four, and let's say we allocate them 80% turnout, we look at Central maybe 44% turnout, East maybe 55% turnout, and North something like 60% turnout. Then we are going to go ahead and order this list. And let's say maybe in order we will have Western, Northern, Eastern, then Central. This is ordinal data. If we go ahead and look at interval, here we are talking about data without no true zero. An example, if we say maybe the temperature in the polling stations on election day, and suppose one polling station was at 0 degrees Celsius. 0 degrees Celsius does not mean that no temperature. This is not correct. It is just a reference point. Zero is a reference point. It is not an actual zero in this case. And lastly, ratio data. This is where zero truly, what is a true zero? For example, if we look at the number of votes per candidate for MP, let's say candidate A had 10 votes, candidate B had 100 votes, and candidate C had 0 votes. This 0 would actually mean that no one voted for this candidate. And also, in this case, candidate B has 10 times more votes than candidate A. So, a side note here, if we look at this information at a deeper level, categorically, if we are to go back to categorical data, when we talk to, for example, classifying districts according to their colors. And if we say, maybe these are the figures, not the actual figures. Let's say Uganda has 149 districts. I am not sure of the exact figure, but let's use that for now. And let's say 26 of them turned out to be to like the highest percentage of voter, the highest number of voters turned out to be for NUP, and the remaining 120 turned out to be NRM. And we're to use this data to try to predict the election results. You'll find that 26 out of 146 gives you times 100 would result into, let's say, I think this is 18%. Then 120 over 146 times 100 would result into 82%. So this is one way. So here you're using data to predict. But then now, if we go ahead and we look at the actual figures, let's say numerical district, we go and look at actual votes. Nationwide, if I remember, NRM had, I think, around 7 million votes and NUP around 2 million votes. These are just rough estimates. And we are to, in this in percentage, 7 over 9, that is about 75%, right? Then this is about 25%. So you realize, based on the way you collect and represent your data, you can end up with different figures. So you find that NUP increased from 18% to 25%, while NRM decreased from 82% to 75%. In the first part here, we're using just like the district preferences to determine. And here we're using the actual data, the actual number of votes to determine the results. So the point that I'm trying to drive home is that of content versus context in statistics. Just as we learned in communication last semester, content is the actual figures, then context is the background. In this case, the context is the way I came up with the figures. And if you go on to listen to news, you find politicians using these figures. And sometimes they can use figures in a way that is misleading. For example, saying that 80% of districts prefer NUP to NRM, or say NRM is leading by 82% in terms of district preference. But that is not the actual votes. When we went to the polling station, NRM was taking 75% and NUP 25%. So statistics can be used, is a form of communication actually. And sometimes people can exploit it to try to sort of mislead the attention of the people. Okay. Before we leave the first part of the introduction statistics, we need to look at Charts. Charts, these are illustrations that we use to represent data. For example, a bar chart. Bar chart or pie chart. A bar chart, you have something like this, and with bars. Let me draw it more clearly. So let's say we want to plot MP seats. So let's say this is NRM having the highest, followed by NUP, then independent. Then the rest take this other percentage. This is a bar chart. Alternatively, we could use a pie chart to represent this categorical data here. Maybe, so this is RM. I think it's more like this, I remember. So let's say this is NRM, this is NUP, this is independent, and this is others. So we use them in different situations. But here you can clearly see that a pie chart is better situated to represent this categorical data because you can clearly see who takes more than half and the rest. Are we together? Can I have thumbs up if you're together in the chat? 5%. Oh, nice. Let's go ahead. So we have looked at categorical data. Now let's look at other forms of data. Let's say now we are dealing with numerical data. Numerical data, let's use an example of voter turnout. If we are to categorize, let's say 0 to 30% voter turnout, we had, say, 100 polling stations, 30% to 60%. We had maybe 400 polling stations, then 60% to 100%. We had, let's say, 50 polling stations. And we want to plot this data. You realize that these are two forms of numerical data. We have voter turnout for the elections, then we have number of polling stations. So if we wanted to plot this data, the appropriate chart would be a histogram. So we'd have here our 0, maybe our 30, our 60, and 100. All these are percentages. Then we go ahead and we have our scale, 50, 100, 150, like that, and here we have 400. So if we want to plot this data, we shall end up with, for the first polling session, we have 100. For the second, we have 400. And for the last, we have 50. So this data would be a histogram. Hopefully we are following. So sometimes it's confusing to know when do we use which form of chart. Let me clear this. Let me proceed. Okay, let's move to the last one. Scatter plot. So a scatter plot is used to study the relationship between two numerical sets of data. Remember, histogram works in a situation whereby one of the numerical sets of data is grouped. Like as we saw with percentage voter turnout, we saw that we grouped it in 3 categories: 0 to 30, 30 to 60, and 60 to 100. Now, a scatter plot, let's say we wanted to know that what is the relationship between income of voters and maybe income. No, let's say we want to study what's the relationship between average income in a given district and percentage of votes for NUP. If we want to study which people have a preference for NUP. Is it the rich? Is it the middle class? Is it the poor? So in this case, we go ahead and build a scatter plot. Scatter plot to accesses. One axis which here we shall put here average income. Then here we put percentage votes for maybe NUP. And we start to plot. So let's start with maybe Kampala. You know that Kampala is the people in Kampala have in Central General have the highest income. And if we are to plot it, you find it here. They have the highest income and the turn-up was at 64%. Then if we go ahead and look at maybe an region like Karamoja, find that Karamoja, the income is low. However, the voter turnout, the percentage votes for NUP also were listed in such region. And if we go ahead and fill, you end up with something like this. Find that the dots are here. And now, based on this, you're able to draw a line in between the points that tries to represent the data. And you realize that there's a direct correlation between the average income and the percentage votes for NUP. This, of course, you'll end up with certain outliers. For example, if you go to Western, you find that their average income is high, but the percentage of votes of NUP is relatively low. So you find them in areas like that. So this scatter plot I saw it in a certain video. It was during election time, and they were saying someone was trying to make a joke about it that those who are protecting the gains are again the ones who have less to protect. Okay, going forward, let's now move on to central tendency. So this central tendency, we are basically trying to find the typical value. So the typical value in a given data set, typical value. And if we remember during the first discussion, I defined statistics. And one of the aspects of statistics is summarizing. So you cannot go around moving with the number of votes who turned out for each polling station in the country. So instead, we decide to carry out a measure of central tendency that summarizes the whole data and gives you a single figure. For example, average percentage vote turned out nationwide, which was about 50%. If you're following the election, you know that the average voter turnout was about 50%. 21 million Ugandans were registered to vote, but about 10.5 appeared and voted that day. So you could not move around saying that, I know for all the 100 and maybe 146 districts in Uganda, you know all the number of votes who came and all that. So you decide to get one, decide to summarize it. And one way can be using average, which is the mean. Other ways can be the median, mode. And we are going to look at when do we choose what. So let's start with mean. So mean is simply the average. And it's calculated as summation of n, summation of x over n, which is the same as the total divided by number of items. This is the mean. And that's how we have always calculated at all levels. And mean works well for symmetric data. For example, the one I've given, the average nationwide voter turnout was 50%. Also, so we know this works well for symmetric data. However, one issue with mean is that it's affected by outliers. At this point, let me define outliers once again. Outliers, like for example, if you are to look at maybe, let me just come back to agriculture. If you are to look at maybe the output over a period of maybe 10 years, maybe from 2015 to 2025. Once you look at maybe the coffee output in Uganda, and we'll go ahead and plot it, and you realize that the data almost makes a straight line, but then 1 year it decides to go and it comes back up. This point where it changes so much than the rest is an outlier. Maybe this year there was famine, maybe there was war, maybe there was COVID, whatever. That would be an outlier. So going ahead, let's look at median. So median is simply the middle value. Middle value of ordered data. Remember, if you're to find the median, the data has to be ordered. So in a situation where a significant number of outliers exist, mean may not provide a good representation. So we choose median as it's resistant to outliers. Median is resistant to outliers. Remember, outlier is that data say that varies so much from what we expect from the norm. That is an outlier. And also, in a situation where the data is skewed data, it's maybe that how text is shaped. Okay. Let me show you 3 illustrations. So we have this, we have this, we have this, and then we have this. These are 3 shapes of data. Oh, it's not clear when the data during this. So this is right skewed, right? Skewed. This is symmetrical data, and this is left skewed. So data can take different shapes at times. So in this case, this was right skewed, it's symmetrical. Now, when you have symmetrical data, the appropriate one here is the mean. But now when you have such data, the better one to use is the median. Hopefully we understand the difference. Mean works well for symmetric data and is affected by outliers. However, where we have skewed data, the appropriate one is the median, or where we have outliers also, the median works so well. And the other one that we can look at is the mode. And mode is simply the most frequent value. Most frequent value. An example would be if we group district election results by color party. For the MP elections, we shall see that NRM has the most number of seats in parliament. So the model party was NRM. Okay. Now, having known the central tendency, let's go ahead and look at variations. So you realize that it's not enough for you to know just the central tendency. They need to provide the context. As I mentioned earlier, context. This is where variations come in. For example, it's not enough for you to know that the average voter turnout was 50% in the national elections. You also need to know by how much standard deviations does the average voter turnout vary from the mean. You want to know that. Was it, or how consistent? Variations, basically, you want to see the consistency of your data. How consistent was it? So the simplest measure of variation is range, which is simply the maximum minus the minimum, and it's the easiest to calculate. However, it's affected by outliers, so you have to take note of that. Then when we look at variance is calculated as the summation. So there are two variants. There's one for sample and there's one for population. Let me give them for a sample first. The summation of x minus mean, all of this square, divided by n minus 1. Whenever you see small n, we are talking of a sample. Then for population, variance is calculated as x minus mean squared divided by n. So take note of this. When I talk of sample, like in this first case, this is sample and this is population. So sample we divide by n minus 1 as a correction because we are working with a small data set. So this minus 1 is a correction. If you remember errors, sources of errors, correction n minus 1. Then here, because we are using the actual population, we use divide by n. Okay. Are we together up to that point? Actually, any questions? I would like us to ask any questions you have so far. We have looked at introduction to statistics. We have looked at measures of central tendency, and we are now on variation. We have covered up to variance. If you have any question, feel free to ask in the chat. Feel free to unmute and speak. Any questions? All right. I will take the silence to mean that we are all at par. After standard deviation, after variance, okay, more on variance. So variance for a sample, variance for a sample is calculated. Sample variance is calculated as summation of x minus mean divided by n minus 1. Now to calculate, if you remember in your N level or O level, wherever, when we're learning about this, we would draw a table. So you start with your data. Okay, you have to first calculate the mean. You need, because it's a single value for all data sets. After you've got the mean, this represents the mean. For example, the mean is written as this, mu. Right. Then for a population, it is written as x bar. Let me start first from the difference between population and sample. When we are doing statistics, there are two types of data that we can use. We can use data from a population and data from a sample. An example of population would be census. If we carry out a census where we go home by home and talk to every person, that would be the data we collect is from a population. However, when we do a survey and we speak a few people and we ask them questions, and we use that data to represent the whole of the population, that would be sample data. So we have population and sample. A variance, for it, you just have to know the formula, how it's got. And it is the summation of x. X are your values, minus the mean of these values divided by, okay, this is squared. You first subtract, then you square, then you divide by n minus 1. Okay. So let's have a look at how we get this with a table. So in our table, you have a column for x. You have a column for x minus mu. Then you have another column of x minus mu squared. Then the summation of x minus mu squared is what you use to calculate the variance. So let's say our values are 2, 6, and maybe 8. And our mean is 1. Or let's use bigger values. Say our values are, okay, this our values are 1, 2, and 4. And our mean is equals to 2. This is our table. So our first step will be to calculate our x minus mean. Our mean is 2, our x values. So 1 minus 2, what do we get? We get minus 1. 2 minus 2, we get 0. 4 minus 2, we get 2. Then we go to the next step where we square. 1 squared, we get 1. 0 squared, we get 0. 2 squared, we get 4. So in this case, our summation of x minus mu, all of it squared, would be 4 plus 0 plus 1, which is 5. So our variance would be 5 divided by number of items is 3 minus 1. So our variance would be 2.5 in that case. Okay. Hopefully we are together now. Let's proceed. To standard deviation. Deviation, sometimes called SD, is simply the square root of the variance. So after you've calculated your variance as shown above, its square root gives you the standard deviation. And so you will notice that both SD and the variance are affected by mean. What does this tell you? Remember, we say that mean is sensitive to outliers. So if SD and variance are both affected by mean, that means they are also sensitive to outliers. Because in the formula of variance, there is mean. If you look at the formula of variance, you will see that you will subtract the mean from R. Let's go ahead and look at the quartiles. So quartiles, we have the first quartile Q1, which is the 25th percentile. We have the second quartile Q2, which is the median. We have the third quartile Q3, which is the 75th percentile. And if we are to proceed, we look at this concept of interquartile range. So interquartile range is simply the difference between the third quartile and first quartile. So this is a method of calculating what? Is a method of calculating range, interquartile range, but instead of using the highest and lowest values, we use the third quartile and lower quartile. If you remember, there's a concept called the 5-number summary, where we have the minimum value, we have the first quartile, we have the median or second quartile, then we have the third quartile, and we have the max value. If the data has outliers, this is a term we shall be using a lot. Outliers, you have to understand it. If you've not understood it now, you can try using your AI later after to understand it better. But what I can say is outlier is the value that does not match the rest. For example, if we are to plot data maybe, and you find that the data is moving like this, then suddenly it drops down. This last value is an outlier. Or if you are plotting points on a graph and you have points like this, then suddenly one value is so high. This is an outlier. So range uses max minus mean. That means it's very easily affected by outliers. However, interquartile range uses Q1 and Q3, so it's less affected by outliers. For the methods of calculating this, you can refer to the first discussion. I shared with you a link earlier on the recording of that discussion. I would like us to move so in the next let's look at coefficient of variation, which is simply SD over mean times 100. Let us say we want to compare the variations of water turnout between Central and Eastern Uganda. We look at the mean, we realize that the means are different and the SDs are also different. So if we want an accurate way to compare their variations, we look at the coefficient of variation, whereby we calculate the SD and divide by the mean for Eastern and for Central. And then the one with the higher coefficient of variation means that the water turnout varies by much across different polling stations. Okay, that is our revision of what we covered in our first lecture. And it's exactly 40 minutes past. Now let's go ahead and look at what we came to cover today in the next hour and a half. And today, our goal is to learn about normal distribution. So this concept is a little technical. I ask you to pay attention and ask questions. Don't allow to get lost for long. If you immediately want to stop understanding, feel free to unmute and ask a question or type your question in the chat. I keep checking on the chat to see if there are questions. I will start first by mentioning that if we are to, for example, in our class, if we are to measure the heights of every student, and we go ahead and plot a graph of, and we group them, let's say, for every value, maybe those who are 175 centimeters, 120 centimeters, all like that, and we group that data. And we go ahead and plot a chart of height against number of people in that height category. We realize that we end up with let's say this is our graph, and we want to plot height, then number of students. So from the short ones, you realize that they are 1, 1. Then until we reach the average, well, we see that has the highest number and continues dropping, and you find the total powers of you. So we end up with something in this shape, a bell-shaped curve. The same applies if we are to plot the edges, if we are to plot maybe the sleep times and different data. So you realize in life, so many things fall into a bell-shaped curve. And this bell-shaped curve is called a normal distribution. There's a number of unique things about a normal distribution that we shall come to learn about later. So to start with, properties, normal distribution, we know that it takes the shape of a bell-shaped. And also, the data is symmetric. You realize that this side is the same as this side. Also, the mean, what is mean? Mean is the average, which is somewhere here in the middle. The median, which is the middle value, then the highest value, which is the mode, all coincide. You find that the mean is equal to the median, which is equal to the mode when it comes to normal distribution. Then it has two parameters you consider that is the mean and the standard deviation. Whenever I want to represent a normal distribution, these two parameters are important. The mean and standard deviation. Let's go ahead. For a standard normal distribution, which is denoted by Z, the mean is always 0 and the SD is always 1. So for a standard normal distribution, the mean is 0 and the SD is 1. So here in the center would be 0. So going this side would be negative 1, negative like that, negative. Then going this side would be positive, positive, positive. Then the Z score. The Z score is simply a way of converting an ordinary distribution to a standardized distribution. It's the method of standardizing a distribution. And to come up with a Z score, we say that Z is equals to our value minus the mean divided by the ST. Don't worry if this is confusing. Right now, it's all going to become clear as we go ahead and do some examples. So, empirical rule states that 68% lies within one standard deviation, 95% lies within two standard deviations, and 99.7% lies within three standard deviations. So if we have this as our curve, one standard deviation would cover maybe this data. This would be 68% of the data. If you do standard deviation, two standard deviations, it may cover, let's say, this data like this. And this together, if you were to add it up, it adds up to 95% of the data. And if you do three standard deviations, you end up with this, which covers maybe 99.7% of the data. I shall get to understand this as we go on. And sometimes you will be given the standard normal and you'll be required to go back to the probability. For example, in this case, so if our standard Z is equals to X minus mu divided by SD. If we want to find Z, we take this here. So Z theta is equals to X minus mu. So our X shall be equals to Z theta minus our X will be equals to mu plus Z theta. Hopefully this makes sense. Then we shall look at normal approximation to binomial. Okay. So in an exam, you would be given two charts. One is a cumulative positive chart, which covers values after the remember for a standard normal cumulative probability table or a standard normal distribution, the mean, median, and mode are all equal to, okay, we normally consider the mean is always equal to 0. And the total area under the graph is the probabilities, and this adds up to 1. So remember, total probability, which is the area under the graph, adds up to always 1. And find that the value, so that means that remember this is symmetrical, that means this side is equal to this side. So that means here the total on the right is 0.5 and the total on the left is 0.5. So this total shaded area 0.5 and also here 0.5. So 0.5 plus 0.5 gives you 1. So when we are using the standard normal cumulative probability table to come up with values, we can have positive values and negative values. Bear with me, this is looking confusing. That's why I began first by going through what we covered before. Because this normal distribution is somehow technical, but if you pay attention, you should be able to understand. So the positive one, as you can see this diagram here, it shows the ones which come after. You want to find the probability of a point after the mean of 0. So for example here, let's call this a point X, and you want to find the Z value, which is this. So you come and read the table. And if I zoom in, you realize that we have here different values. So this is the Z value. You read it as 0.1, then you add 0.1, maybe 1, 0.1, 2, 0.1, 0.14. Let's say 1.3, 1, 1.30, 1.31, 1.32, like that. That is how the information is read. This that is appearing inside these values here are the actual X values, which is the probabilities. The Z value is the one on the columns, the X value is the one inside. Hopefully we are getting that. And so for there are two tables, there's one for positive and for negative. So for positive, it goes beyond the mean. For negative, stays before the mean. This one here is clearly for negative. Let's go ahead. So probability distributions, commonly used in business, can be divided into two. We have discrete and continuous. Under discrete, we look at the binomial. Remember, reporting day is Tuesday. Normal and uniform. So today we are covering continuous. So let's go ahead. Don't worry, if it has been confusing, you're going to understand it before the end of the lecture. And if you have any questions along the way, feel free to unmute and ask your question. Feel free to type your question in the chat. I'll be able to respond as soon as possible. So today we are going to our focus areas include calculating Z scores and probabilities using the Z table. We're going to apply this table to calculate Z scores and probabilities. Then we're also going to use it to solve inverse normal problems, finding X given the probability. Maybe they tell you the probability of a farmer maybe harvesting more than 50% is 0.9, and they ask you how many farms for that harvest. After looking at inverse normal problems, we are going to move and look at applying empirical rule, whereby we know that 68 lies within one standard deviation of the mean, 95 lies within two standard deviations of the mean, and 99.7 lies within three standard deviations of the mean. Then lastly, we shall look at using normal approximation to binomial when appropriate. So in the exam, you should be able to visit okay, let's go straight. So standard normal distribution. Z is equals to X bar minus mean divided by standard deviation. And here we have example 1. So like always, I'll go through the examples, explaining, answering questions. Then when we reach the quiz, I'll ask you people to step in and answer them. You can talk, turn on your mic, talk, and I write. If you can type the solution in the chat, you can do that. Whatever, but I encourage you to talk. Actually, we're all on the same level, so why not? Feel free to talk as long as you're clear and audible. Our number 1 is saying maize yield in a region are normally distributed. Maize yields in a region are normally distributed with a mean. So we write the mean. Have told us is 1,500 kilograms per acre, and the standard deviation of 200. And then they're asking us calculate a farmer harvests. So that's our X value, 1,800 kilograms per acre. Calculate the Z score and interpret. So the maize yield in a region are normally distributed with a mean 1,500 and standard deviation 200. A farmer harvests 1,800 kilograms per acre, and they're asking us to calculate the Z score. Can I see in the chat anyone who has an idea what you're going to do? Yes, just an idea. You can unmute, you can type in the chat. How do we go about this question? Okay, to save time, let me do this, then we shall discuss, we shall do together. You will do the quiz. So, means yield in a region, normal distribution, we have the mean, we have the standard deviation, and the X value, so the one, the Z score. So, when you look at this formula, we have the standard deviation, we have the mean, we have the X value, and the one, the Z score. So, write the formula. Z is simply X minus mean divided by sigma. Put this in brackets. Catching up so a bit fast. So substituting shall have 1,800 minus 1,500 divided by 200, which is the standard deviation. So Z shall be equal to, I think you get 300 up here, divided by 200, which is 1.5. And our conclusion is that the Z score and interpret. So our Z score is 1.5. That means that Z is 1.5 standard deviations. Because it's positive, we say above the mean. If it was negative, we'd say below. So the question was asking that we calculate the Z score and interpret. We're given the mean as 1,500 kilograms per acre, the standard deviation as 200 kilograms per acre, and the X value, which is 1,800 kilograms per acre. And they want us to calculate the Z score. So we did what we did, we got the formula, substituted, and ended up with the Z score. Are we together? Any questions before we go ahead? Yes? Okay, I proceed. So Z score tells how many standard deviations above, which is positive, or below, which is negative, the mean. Interpretation is often required for full marks. Units cancel out. So the units kilograms per acre cancel out. So Z score has no units. Let's move on to number 2. We are going to now be using the table. So find probabilities using Z table. The rule is that we use the table to find the probability for Z less than Z, then adapt for greater between etc. Example 2. Using example 1 distribution, what percentage of farmers harvest less than 1,800 kilograms per acre? So using this data of a farmer maize region, the mean being 1,500, standard deviation being 200, a farmer harvesting 1,800. What else to know? That's just, they want to know what percentage of farmers harvest less than 1,800. So from example 1, our Z value is equals to 1.5. So what we'll, after we've got the Z value, we go to the table and we see where does it lie. Where in the table does, what is the probability that corresponds to 1.5 Z value? So 1.5 is positive, so we will not be using the negative table. So we go to the positive table and we go to X, Z, this is Z actually, not X. Zooming one, this is Z. So we look at 1.5. If you come here, so we get 1.5 is here. This is the row for 1.5, but now we are saying 1.50. So we take the first one. If it was 1.51, we take this one. But in this case, what we require is 1.50. So It's clearly highlighted here. Our Z values our Z values 0.1, 1.5 is here in red. And are we together? Is the screen moving? Hello, are we together? Okay. So looking at this, you find that Z correspond 1.5 corresponds to 0.9332. Okay, so let's go ahead. So probability of Z, this is cumulative, so we say less than 1.5 is equals to 0.9332. Probability of Z less than 1.5. We saw it here. So Z, if you put here 1.5, probability of Z less than 1.5 is all this region, which is shaded, which comes to 0.9332. Okay, let's go ahead. Our question wanted the percentage of farmers harvest less than 1,800 kilograms. So we have found the probability to be probability of less than 1,800 kilograms, which corresponds to Z score 1.5 being 0.933. So for percentage, is simply probability times 100%. So 0.9332 times 100%. This gives us 93.32%. This is our answer. Are we together? Yes, are we together? Any questions? Any questions? Okay. Let's proceed. Now, what we did, we got the Z score 1.5. We went to the table and we got the probability, which came to 0.933. Then I got the percentage by multiplying probability times 100%. And our answer was 93.32%. They may ask for more than between or outside. Remember, probability of Z equals to 1 minus probability of Z. So if you have to convert from, let's say probability, like in our first example, let's say 1 probability of Z greater than 1.5. What we calculated was probability of Z less than 1.5. And now if they ask for probability of Z greater than 1.5, we shall say 1 minus, let me sketch for you first. So this is a normal distribution. This is the mean, and this is our point of 1.5. And we got the probability of Z less than 1.5, which is the shaded region. Probability of Z less than 1.5 as 0.932. Now, what if they ask for probability of Z greater than 1.5? What do we do? Let someone answer the chart. In our first step, we wanted less, and we got it as 0.9332. Now, what if they ask for greater than? What would we do? Anyone? Yes? Anyone with an idea?
Yes. Good evening.
Good evening, Nico.
Yeah, before rubbing that thing you've rubbed, could you please take it back? I think when you're drawing that thing, where you put the 1.5, you're supposed to put there the probability, which is 0.9332.
Is this what you mean?
Yeah, we are supposed to put there 0.9332 because those are probabilities. I think we don't have a probability that is greater than 1, not so?
No, this is the Z
Yeah.
score.
So my
The
idea
probability-
is, I think, yeah, my idea is,
Go
I
ahead.
think we put there like it's equal to 1 minus probability of Z less than 1.5.
Okay. Which will be equal to 1 minus 0.9.
0.9332.
Okay. I think this gives us 0.06. No, 668. Okay. Thank you, Nico. So what Nico has shown us down here is correct. If they ask for less, it's 1 minus. I mean, if they ask for more than, it's 1 minus less. Remember these symbols. This is less than, this is greater than. And here, correction, Nico. This point shows the Z values. This is the Z axis. So here it's 1.5. It's not probability. Probability is the shaded area, which is here. So this shaded area, if you were to calculate it, you would end up with 0.93. 0.9332. Okay, so we are together. All right. So thank you for that. Let me clear this and I choose number. So let's say they ask us to calculate the probability the probability between 1.2 and 1.5. So given that the Z score lies between 1.2 and 1.5, they ask us to find the probability that Z lies between 1.2 and 1.5. We already know what. Okay, so for this case, we shall need to first calculate probability of Z greater than 1.5. This tab here. And Nico has told us that this is the same as 1 minus probability of Z less than 1.5. Don't worry, I'll share with you these notes when they are more clear. Right now, my pen is disturbed. And this is 1 minus 0.9332, which gives us 0.0668. All right. This is limited in this case.
Yeah, excuse me.
Yes?
I have a question. First wait.
Okay.
Yeah, about that thing you're doing, we found the probability of Z is greater than 1.5. I've thought you're supposed to use the probability of Z is greater than 1.2 and the probability of Z is less than 1.5.
Yes. We are going, yeah, greater than 1.2 and less than 1.5, right?
Less than 1.5.
Actually, you're right. So we don't need this step.
Yes, okay.
Thank you for that observation. We are finding the probability that the Z score is between 1.2 and 1.5. That means greater than 1.5 but less than 1.2 but less than 1.5. So we should calculate the probability of Z greater than 1.5. I mean 1.2, which will be 1 minus probability of Z less than 1.2. Why we do this is because the table only shows less than. So we always, if we are asked to calculate greater than, we convert it to less than. And if we go to our table to 1.2, our probability of z less than 1.2 is 0.8. This is 8849. 8849, yeah. So when we substitute, probability of z greater than 1.2 will be equals to 1 minus 0.8849. Okay. Which will be 8849. 1 minus 0.8849, which is 0.1151. 0.1151. Nice. And we know our probability of z less than 1.5 will be 0.9332 from the earlier example. So the probability of z being between 1.2 and 1.5 will be equal to probability of z less than 1.5 minus probability of z greater than 1.2, which is equal to 0.9332 minus 0.1151. 0.9332 minus 0.1151, which is 0.8181. So our probability of z being between 1.2 and 1.5 is 0.8181. Is this okay? Okay.
Excuse me.
Yeah.
Could you please help us explain using a diagram where we're subtracting?
All right.
Okay.
Let me get back. So let me use this space. So we have two z values. We have, let's first put the mean. This is our mean of 0. So we have two z values. First one is 1.2, and the second one is 1.5. And they're asking us to find the probability of z being between 1.2 and 1.5. Probability 1.2 is greater than z, which is greater than 1.5. Simply means probability of z being between these two, which is this area. So to find that area, we shall go through two probabilities. The first one is probability of Okay, small challenge there. Let's continue. We are, as Nico asked, we are finding the probability that Z lies between 1.2 and 1.5. So what we do, we shall find first the probability. This is probability of Z less than 1.5 and probability of Z greater than 1.2. When you subtract this from this, you end up with this. Are we together? So we found the values. Probability 1.2 less than Z less than 1.5 is equals to probability of Z less than 1.5 minus probability of Z greater than 1.2. Probability of Z less than 1.5 is 0.9332, and this was, I think, 0.1151, and that gave us our answer. Okay, let's go ahead. Now that we have looked at that, we are going to now look at inverse normal, where we are finding x given the probability. And this is the formula we use of x being equal to mean plus z theta. How does this come about? Remember, our z score is x minus mean divided by theta. Now, making x the subject, we shall take this inside. So z theta will be x minus mean. Making x a subject, still we take this side. So z. So if you take mean this side, it becomes positive plus z theta is equals to x. And if we start with x, we end up with, are we together? Sigma, not theta. Sigma. Are we together on how we end up with this formula, inverse normal formula? Okay. Now let's attempt this question. The maize yield in a region are normally distributed with mean, telling us the mean. The mean 1,500 and standard deviation, which is sigma 200. Find a yield that only 5% of farmers exceed. So that has to find the yield that only 5% of farmers exceed. All right. Remember, in the earlier question, we were given mean, we were given sigma and x. But this time, we are, instead of x, are giving us the probability. So our steps are, if we're using the probability, we are going to find the z-score. Then the z-score will lead us to the mean, to the value of x. So in the first examples, we're given x and we wanted the probability. So we first got x and standardized it, end up with a z-score. Then from that, using this, we use the table. Then from using the formula, we're able to get the probability. But this time, they're asking that we go reverse. So we're using the z table, we shall find the z-score. Then using the formula, we shall find x. So let's follow together. So we go to, in this case, they're asking probability of find out the yield, find the yield that only 5% of farmers exceed. So exceed means greater than. So Z, we are finding X. Let's call it X. For 5%, that's the same as 0.05. And they've told us in brackets, i.e. 95% are below. So they're trying to make your life easy. So you go, probability of Z less than X is 0.95. If they didn't tell you this in bracket, you could also calculate it as 1 minus 0.05. We are just changing the direction. So we say 1 minus. Because less is what appears in the cumulative table. They don't show above. So now that we know this, we go ahead to our cumulative table and look for the probability 0.95. And we see what Z value it corresponds. Actually, you see, we are not yet at the step of Z. Let's call this Z1 and Z1. Or small z, whatever you choose. So we're given the probability, they want us to find the x. And we are going to first find the z value, then using the formula, find the x. The z value, we shall find it using the table. So we go on the table and under the probability section, we shall look for a value that corresponds to 0.95. So if we go to this table, positive, and they're telling us 0.95, so we start looking where 0.9 is around here. I'm seeing here 0.939495 is here. So there are two values here. I don't think you can see it, but let me try to zoom. So there are two values here. We have 0.9505 and 0.9515. 0.9505 and 0.9515. Which of these is closer to 0.95? The first one, 0.505 or 0.9515. Can I see the answers in the chat? Which of the two is closer to 0.95? Yes? Okay, the first one. Yeah, so if we subtract here, we get 0.0015, here we get 0.0005. So we take the first one. So now to read the value, you can do. Wait a minute. So there are two values. It lies 0.95 lies between 0.9495 and 0.505. And for me earlier, I chose to use 0.495 instead of 0.9505. But it doesn't matter, the difference is small. So if we are to use 0.9495, which is approximately 0.95, and we are to read the z value, so we first come horizontally, which is 1.6, and then we see the third value from up here, which is 4. So 1.6 plus 0.04, which is the same as 1.64. Altogether, the value which is closer, which I chose earlier, was 0.9495. Because 0.9495 and 0.9505 are all 0.005 away from 0.95. So any you pick is okay. In my preparation, I chose the first one. So it corresponds to 1.6 plus 0.04. If you chose 0.9505, it will be 1.6 plus 0.05. So our answers are 1.65 and 1.64 and 1.65. So for this example, I'm going to be using 1.64. So that means the Z value, our Z1, will be equal to 1.64. Now that we have our Z value, we are going to apply this formula, the inverse normal formula, which is X is equals to mean plus Z sigma. Our X shall be equals to, our mean is 1,500, our Z is 1.64, and our sigma is 200. If you do the math, our answer should be 1829 as our Z value. So the answer is 1829 kilograms per acre. Always remember the units. All right. So what we did, the first thing we did was we want probability of Z less than 0.95. We are looking for the small z. So from the table, the Z table, Z for 0.95 is approximately 1.645. And in that case, our X, and we then, after we have found the Z value, as this, we substitute in this formula of X, the inverse normal formula. This is our mean, this is our Z value, and this is our standard deviation. And our answer comes to 1829 kilograms per acre. Inverse problems. The first step, you have to find the Z score corresponding to the given probability. Careful with direction. Then use the inverse normal formula, which is X minus, which is X equals to mean plus Z sigma. Okay. Next, we shall look at our empirical rule application, where we know that our one standard deviation from the mean, which is mean plus one standard deviation, plus or minus one standard deviation, covers about 68%. Mean plus or minus two standard deviation covers 95%, and then mean plus or minus three standard deviation covers 99.7%. And here is an example. Cattle weights at a farm are normally distributed with a mean of 500 kilograms and standard deviation of 25 kilograms. What interval contains the middle 95% of the weight? What interval contains the middle 95% of the weight? So normally, without the knowledge of empirical formula, how would go and find this? Would start first by getting the middle 95%, which corresponds to 2.5% and 97.5%. Then you find the Z's, because these are probabilities. This converted to probability would give you 0.025 and 0.975. And then from this, we'll look at the table and find the Z squared. So we find maybe Z1 and Z2. Then from there, we'll go ahead and find the what? Find, using the inverse formula, we find the values of X1 and X2. And with that, we'll be able to determine the interval in kilograms. This to this, dash kilograms to dash kilograms. But now, with our knowledge of empirical rule, when we see 95%, we immediately think of two standard deviations. So instead of using this formula, we shall go ahead. Let me put this aside for this aside for reference. Okay. When we see 95%, we just go here immediately and we think of two standard deviations of the mean. So the lower value would be the mean minus 2 sigma. Our mean is 500 minus 2 times 25, which is 450 kilograms. our upper value, we use plus our main class to sigma, which is 500 plus 2 times 25, which is 550 kilograms. Therefore, the middle Wow. I've been going with my mic muted. All right, let's go back. Okay. So, if we were asked without the knowledge of empirical rule to find the interval containing the middle 95% of weights, so we would go ahead and we know middle 95% lies between 2.5% and 97.5%. and we'll go ahead and convert those to probabilities, which is 0.025 and 0.975. And using our table, we'll be able to reverse and find the z-score as z1 and z2. And using our inverse formula, we'll go ahead and find x1 and x2. And our final answer will get for maybe dash kilograms to dash kilograms. But now, with our knowledge of empirical formula, we don't need to go through all those steps. There's a shorter way to go about it, and that's using the empirical formula. When we see 95%, we immediately think that these are two standard deviations. So the middle 95%, these are rules, so you have to master them, lies between mean plus or minus 2 sigma standard deviations. So the lower will simply be equal to 500 minus 2 times 25, which gives us 500 minus 50, which is 450. The upper one would give us 500 plus 2 times 25, which is 500 plus 50, which is 750. So our answer would be 450 to 750 kilograms. So the empirical rule gives quick approximations without the Z table. It's commonly tested for middle percentage or within questions. You have to watch out for the approximately wording. For you to use empirical rule, the question must ask for the approximate value. Now let's move on to the last part for today, and that is normal approximation by norm. As earlier you saw this table, probability distributions can be divided into discrete and continuous. Under discrete, we have binomial, Poisson, and others. Under continuous, we have normal, uniform, and others. And these two, binomial and Poisson, we shall be looking at them in our next discussion, which is on Sunday. So Sunday, I believe it will be we shall look at binomial, Poisson, then we shall also look at what we left out, which was the correlation, covariance, and lastly, Excel. I'll be showing you people how to use, I'll be sharing with us how to use Excel to come up with some of these figures. Microsoft Excel. It's part of what we cover. So when we binomial, skip binomial, but we have one thing to know is that when we are dealing with binomial basically talks about success or failure. We are looking at probabilities of success or failure. For example, here in this example, we're talking of germination. A seed company claims 80% germination. Out of 100 seeds planted, what is the approximate probability at least 75 germinate? So here, the seeds can either succeed in germinating or fail to germinate. So for binomial distribution, this is an example of binomial distribution, but we're going to apply concepts of normal distribution. For binomial distribution, the mean is simply number of trials times number of successes. And the variance, VAR, is number of trials times number of successes times number of failures. And we know our ST is always square root of variance. So our ST will be number of trials times number of successes times number of failures. We know failures are the same as 1 minus trials. So our ST shall be equal to number of trials, number of successes times number of failures, which is 1 minus number of trials. Probability of trials, probability of successes. Our mean is number of trials times probability of success. Our variance is our number of trials times probability of success times probability of failure. Our SD is simply the square root of variance, which is the number of trials times probability of success and probability of failure. And this can also be written as number of trials times probability of success times probability of failure, which is the same as 1 minus probability of success. Okay. And you can tell this formula is the same as this one here. Square root of number of trials times probability of success times probability of failure, which is the same as 1 minus probability of success. Hopefully we are together. Any questions so far? No question, let's go ahead. They said the company claims 80% germination out of 100 seeds. What is the approximate probability at least 75% germinate? So we know our trials are 100. Our successes 80 over 100 to 0.8. Our our mean is 100 times 0.8, which is 80. Our standard deviation, because we're doing with normal, we need mean and standard deviation. So our standard deviation would be square root number of successes, probability of success, and number of failures, which is the same as 1 minus, and probability of failure, which is the same as 1 minus probability of success. So this gives us square root of 100 times 0.8 times 1 minus 0.8. And this gives our sigma as 4. If you calculate this, end up with 16. Square root of 16 is 4. So for at least 75 by normal approximation to binomial. So we want to calculate this probability. It's a binomial probability, but we are going to use normal approximation. Why? Because it's easier to use. So if you go back to this table, you realize normal is continuous, binomial is discrete. So for you to move from discrete to continuous, there has to be a continuity correction. So using continuity correction, we know for at least 75x is greater than or equal to 75. Using continuity correction, our x greater than or equal to 75, we subtract because it's greater or equal to, we subtract 0.5 for continuity correction. So our x greater than 0.5 will be 74.5. And now our z value will be x minus b divided by sigma. Our z will be 74.5 minus 80 divided by 4. And our answer z will be minus 5.5 divided by 4. Minus 5.5 divided by 4, which is the same as minus 1.375. So going ahead, our probability of z greater than or equal to minus 1.375 shall be equal to 1 minus probability of z less than minus 1.375. So we go to our table to find this. 1 minus probability of z less than 1.35. So in the previous examples, we have been using the positive table. Now for this example, we shall be using the negative table. So we go up here, negative, cumulative, negative. Cumulative probabilities for negative. Z values are shown in the table below. It's clearly written here. Cumulative probabilities for negative, Z values are shown in the following table. If we go to the first one, it says cumulative probabilities for positive Z values are shown in the following table. Remember, always in the exams you will be provided with this table. So it's up to you to know what to do with it. So negative 1.375 come here. Negative 1. So we have here negative 1.3. Negative 1.375 is approximately equal to negative 1.38. So negative 1.38. Let's go to it. Let me draw here a line so that it's clear. Negative 1.378. So negative 1 point. No, sorry. Our Z value was negative 1.375. So we go to 1.3, which is somewhere 1.9, 1.3 is here. So if you draw a line, this is 1.3. It's not clear, but the one we get in the exam will be clear. 1.3. Then 75 is same as 8. And 1.3, isn't this one 1.1? Yeah, 1.3 are the ones above. Then 1.375. So 75 is here. 1.37 lies between these two. So we take 1.378 because 1.375 is approximately 1.338. So we are taking 1.38. 1.38. Our value will be 0.838. 0.0838. So if we continue 0.0838 down here. So 1 minus 0.0838. 9162. This would give us 0.9162 as a bit of error, negative 1.35. And with that, we can conclude that the answer is approximately 0.9162. So the first step, we summarize the question: trials, successes, and then we got the mean. Then we also got the standard deviation, and for at least to use the continuity correction, we ended up with 74.5. And after standardizing 74.5, we ended up with negative 1.375. And we knew since we're using greater than, we subtract from 1. So 1 minus less than this, which gave us this. And these people used the original answer, but first used the table answer. So because the answer is approximate, so the difference is there. So here, this was our answer. Here, this was their answer. So check conditions first. Continuity. Correction. For at least 75, you use 74. They say at most 75, you use 75.5. they say exactly 75, then you use 74.5 to 75.5. This is a little confusing, but I hope you've got it. So that brings us to the end of the examples now, which in the next 12 minutes, we are going to answer questions. And the first question is, feel free to answer in the chat, feel free to unmute, answer the questions. And the first question here is, why do we standardize to Z scores? Anyone know the reason? Why do we standardize to Z scores whenever we're using normal distribution? Let me go through the answers quickly. No one's going to ask you this in an exam. So we standardize to Z scores so that we can compare different normal distributions and use the standard normal table. So it is because we want to use the standard normal tables. When using normal approximation to binomial, why continuity correction? Because binomial is discrete, normal is continuous. Correction improves approximation. Okay. What does a negative Z score indicate? The value is below the mean. In empirical rule, why is it approximately 95% within two standard deviations? It is a property of normal distribution. The exact value is 94.44% within two standard deviations. Then when would normal approximation to binomial be inappropriate? Okay, take note of this. Number 5. When would normal approximation to binomial be inappropriate? When the n pi, which is the mean, is less than 5, or when the n number of trials times number of failure, when the number of trials and number of success is less than 5, or when the number of trials times probability of failure is less than 5, or when the distribution is very skewed. Now we are going to look at our example, and starting with example 1. I will invite you people to come and do this. What numbers I've done the initial example, our quiz. So quiz 1, coffee beans weights normally distributed with mean 0.5 grams and standard deviation 0.02 grams. Find the probability bean weighs between 0.448 and 0.52 grams. And feel free to unmute and then read us to the number. Anyone? If you get stuck in the middle, we shall help you. Just feel free to start. Anyone? Yes? Are we together? Anyone to help us with this first number? Just try, don't worry. If you get stuck, we shall help you. You can even describe the steps and I'll do the actual calculation. Say the first step is this, and I do it. Just tell me what to do. Are we together? What should I give the steps and then you calculate? Coffee beans weight normally distributed with a mean of this and standard deviation of that. I want the probability that a bean weighs between 0.48 and 0.52 grams. I'll do this first number. So let's pay attention so that you are able to do the next numbers. So whenever you hear normally distributed, the first thing is to write down the mean. Our mean is 0.5 and our standard deviation is 0.02. At times you may be given variance, but standard deviation is the square root of variance. So after we have written those down, they want us to find the probability that the bean seed weighs between 0.48 and 0.5. So here we are given X values and they want us to find probability. So we want to find probability, we have to first find Z. So from the X values, we shall use we shall standardize them using the formula Z equals to, then we shall use the table to find the probability. Are we together? So, Saison, can you help us standardize 0.48? What do I write? Yes, Saison. Using the formula. Let me write the formula. You just substitute mean minus x minus mean divided by sigma. Saison. Substitute for 0.48. What do I write?
You get 0.48.
0.48
Yeah, then minus mean, which is 0.5.
minus 0.5.
Then divided by the standard deviation, which is 0.02.
0.02. Nice. So if you calculate this, 0.48 minus 0.5 equals divided by 0.02. So negative 1. Or z will be negative 1. Okay. Let someone else tell us for 0.5. What do we write? Let's call it z1, 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 then z2. Still x minus mu divided by sigma. What do we write? Another password? Feel free. Ibrahim. Ochen Ibrahim, give us the next part. What do I write? Yes, Ibrahim.
Okay, the 0.52 minus 0.5 out of 0.02.
Nice. Okay. Our answer here. Nice. Z3.
We're good to go.
Yep. 1. When we solve this, we end up with 1.
Thank you.
Okay. So I'll do the table work. So for cumulative probabilities for positive x values, if we are to look at the table, 1 positive, 1 corresponds to 0.843. So this will give us probability of z less than z2 as 0.8413. Then if you look at the negative z table, negative 1 corresponds with, so probability of z less than z1 is equals to probability of z less than negative 1 is equals to 0. Corresponds to 0.1587. This one is positive less than positive 1, 0.841. Okay. Okay. Who can tell us what to do next? I think I'll be deleting this. Wait some space. What do I do? Let me make this smaller. All right, who is giving us the next step? Saison and Ibrahim are finished. Irene, give us the next step. Yes, Irene. Irene says in the chat to subtract the 2. Are we in agreement? Do we subtract? Okay, then let me make it clear. So they want probability of lies between -1 less than z less than 1. What is that probability?
I think is 0.68.
You've subtracted. Have you subtracted? All right, to clarify this once again, when they ask you to find the probability of z lying between -1 and +1, this is the same as probability of z greater than probability of z less than 1 minus probability of z greater than -1. This is what we are finding. So we know the probability of z less than 1 as this, but we don't know the probability of z greater than -1. I don't know. Let's try target for space. We try to clear this. Create some space. Okay. Let me write the things clearly so that we are not confused by it. 0.1387. I think this one is clear. So they're asking for the probability that a bin weighs between these two. And you have already probability of bin weighing between 0.46 and 0.52. First of all, is equal to the probability that the z score lies, the corresponding z scores from -1 and 1 lie between z. And we know that probability of -1 less than z less than 1 is the same as probability of z less than 1 minus probability of z greater than -1. Are we together on this part? Does everyone understand this part? Check in the chat. Okay. So Irene, you continue to tell us what to do. What is our next step from this? How do we find? We have already the probability of z less than 1. How do we find probability of z greater than -1? Probability of z greater than -1. How do we find it? Feel free to unmute. Yes?
Don't we already have it?
The one we have is the probability of z less than -1. What we need is the probability of z greater than -1.
1 minus the probability of z greater than -1.
Okay. So we substitute. So probability of z greater than -1 will be 1 minus 0.1387 8613. So what will our probability of z being between them be? I even continue to guide us.
To be the probability of z less than 1 minus the probability of Z greater than -1.
Substitute. What are the values?
0. Wait. Where is it? Where is that? 0.8613
6413. I didn't write clearly. Minus.
0.8613.
Wait a minute. It's correct. 8613. Moment. I think I messed up somewhere. Where is it? Less than 1. Wait a minute. This is our graph. With 0, -1, and 1. We want this probability. So this is the same as probability of Z less than 1 minus this one. Probability of Z less than. Oh, I think I made a mistake. Irene, you were right at first. Isn't it? I think I made a mistake. Our probability of Z lying between this and this is supposed to be probability of Z minus less than 1 minus probability of Z less than -1. Is this correct? Let me write for what I'm saying. It is becoming technical. Let's clear this down apart. If we follow what we have just been doing now, we're going to end up with a negative answer. And we know probability can never be negative. I think I made a mistake at this level. This is supposed to be this probability of Z less than 1. Let me make it clearly. Probability of -1 Z 1. Okay. Probability of Z less than 1 minus probability of Z less than -1. Why I think so is because if we sketch it, this is our mean of 0. This is 1 and this is -1. +1. If we want this probability, we shall first find the whole probability of 1 less than 0. I mean probability of Z less than 1, which goes up to here. The whole of this, and then probability. Then we subtract the probability of Z less than -1, which is this, and the remaining part would be this. Because if we have this and we subtract this, I don't know, are you getting what I'm saying? Are you following? I made a mistake at first, and I converted, yet we're supposed to subtract directly as Irene had said at first. So the right thing to do, instead of all this that we have done, is that at this level, here, probability of Z between -1 and +1 is the same as probability of Z less than 1 minus probability of Z less than -1. Are we together at this step? Yes? Okay. So our values, we remember them very well. This one was 0.8413 minus 0.1387, and Ibrahim told us the answer is 0.6826. This is the actual working to be done. So now we have gone beyond time. But let's look at this example because this area is looking now technical. Let's be careful with it. Let's look at it, then I'll share with you the work and you revise on your own and get to understand it clearly. So our next number says test score is normally distributed with a mean of 70 and SD of 10. The top 10% get A. Find the minimum score for A. The test scores are normally distributed with a mean of 70 and a standard deviation of 10. Top 10% of scores get A. Find the minimum score for A. Banji, you will be taking us through this number 2. What do we do?
The probability of scoring over A, I don't know. It will be 10 out of 100.
Okay.
And then to get that Z, the like probability of Z and the minimum score for A. Where Z less than 0.1?
Z less than 0.1.
Minus the mean.
Oh, you're using the formula Z equals to 0.1 minus the mean of 70.
Right by standard deviation.
That is standard deviation. Okay, Banji, you mixed up a little. Let's start by first defining our steps. You tell us the steps we are going to do. If you have what do we have? What do we have?
We have the probability. We have the mean.
Okay, we have the mean as 70, nice.
The standard deviation.
And standard deviation as 10, okay?
Probability.
Oh, yeah, you're right. So top 10% get A. What does that? That is the same as probability of Z greater than, let's call it Z1, equals to 10 over 100, which is 0.1. Okay, can now take over from this step. Is that it?
Okay, probability of I don't know, but it's a 0.1 minus the mean. I don't know.
Now, let me give us the rough steps. We have the probability, and we want this the mark, which is the X value. We have to go through the Z score. So from probability to Z score, we are going to use the table. Then from Z score to the value, the mark, we are going to use the inverse probability, inverse. So to use the table, we know that this has to be less than. So if this is less than, how do we write it, Banj? Yes?
What do you mean?
Okay, how do you find probability of Z less than Z1? What is it equal to?
Is equal to 1 minus
0.1, right? Which is 0.9. Okay, now we have the probability. So we go to the Z table. Here we are dealing with positive. Let me see if there's a positive table. So this is the positive table. Our 0.9, where is it? It's right here. You can read the value. Wait, is it 0.9? This is for positive. Z less than 0.9. We go here, sorry. We are given probability. We are going inverse. So we come here, we look, we follow. What is the closest value to 0.9? I can see 0.015 here. I can see 0.8997. Is there something closer? So which of these two is closer, Banji? We have 0.8997 and 0.9015. Which one do we take?
0.8997.
Okay. So taking this, the columns, it's the column, then the row. So you can now read the value 1.2 plus 0.08.
1.28.
Where are we? So our Z1 will be equal to 1.28. Nice. What's our next step?
Find minimum score.
Yes.
I don't know.
So we are given Z. We have been able to find. We are given P, the probability. We have been able to find Z using the table. And what's the next step? To find X. How we go? What are we going to use to find X?
We said inverse.
All right. So the inverse formula Z is equals to. X is equals to Z theta plus mean. What do I write? Substitute.
1.28 times 10 plus 10 plus 70.
70. And this gives us 82.8. Thank you very much, Banji. That's the correct answer. So 10% means 98th percentile. So probability of Z less than small or Z1 is 0.90. And if you use the table here, it corresponds to 1.28. Our second step is to find to use the inverse formula. And when we substitute, we end up with 82.3, which is approximately 83% as the mark for an A. All right. I will guide us through the next number. A survey found farmers' incomes normally distributed in the mean of 1 million and standard deviation of 200,000. The mean of 50% lie between what values? What are we given and what are we finding? Yes?
I'm not seeing that question.
Yeah.
We are given the mean and the standard deviation. What did you ask?
What are we given and what are we finding? Mid of 50%, a survey found farmers' income normally distributed in mean 1 million and SCBs. Mid of 50% lie between what values? So they want X. So You know, we are given probability, but the question is twisted. And we want us to find X. Of course, we have to go through Z. So, middle 50% is the same as 25% to 75%. This is the middle 50%. Okay, so what do? We were given probability, and we have to go to X values. What do?
Onion,
Yeah.
for sure, you just do the number. I'm trying to understand slowly.
Okay. So the question says a survey found farmers' incomes normally distributed with a mean of 1 million and standard deviation of 200,000. And they're asking at the middle 50% lie between what values? They're given the mean as 1 million and standard deviation as 200,000. We know that middle 50%, that is between 25% and 75%. How you do it? You get, if they give you any figure, let's say they gave you, this for 50 is easy, they gave you 68%. You divide it by 2 and you get 34%. Then you say 50% minus 34%. I think that is 16%. That is your lower value. And then 50% plus 34% is 84%. That is your upper value. In this case, we're given 50. So 50% divided by 2 is 25%. 25%. 50% minus 25%, you get 25%. Then 50% plus 25%, you get 75%. Hopefully, we are together on how to find that. Okay, now that we have got that, so 25% is the same as 0.25, and 75% is the same as 0.75. And given these probabilities, and we go and check on the table, if we go to the table and find the probability of Z less than Z1, giving 0.25, we are finding Z1, and probability of Z less than 0.75, less than Z2, giving us 0.75. We are going to use the table to find the values. So they are all positive, 0.25 and 0.75. So 0.25, you have to go. Oh, one thing you have to note, probabilities. This is technical. When you're reversing, you need to know this. So this is the median, which is 0. Anything less than the mean is negative. Anything greater, any Z value greater is positive. So for this case, 0, we know that from 0 up to the mean, the probability from negative Z infinity up to the mean, the probability here is 0.5. So anything less than 0.5 lies this side. Anything more than 0.5 lies this side. Have we got this detail? Anything less than 0.5 is on the left, anything greater is on the right. On the left means it's negative. 0.25 is less than 0.5, so we expect it to be negative. 0.75 is greater than 0.5, so expect it to be positive. Or what you can do, if you forget that, if you go to the tables, if you look at these tables, you realize that the negative one, this is cumulative for negative. Change the color. This is the negative one. The values run from 0.0003 to the highest value is 0.4841. 4841. And if you look at the positive table, the values run from 0.5000 to 0.9998. So we know that for 0.25, it is in the negative table. So if we come here 0.2 is here, 0.25. The closest is 0.2514. 2514, which corresponds to negative 0.6. 0.21. This one here corresponds to negative 0.67. So we write that down. 0.67, negative 0.67. Then we go and look at positive 1. For positive 1, we go to the big table, the positive table. So this is the positive table. So for greater less than 0.75, we look for 0.75, which is somewhere here, 73, 74, 75. I think it's here. Okay, it's also here. And corresponds to 0.67. So this one is positive 0.67. Let me use clear ink. Z1 corresponds to negative 0.67, and Z2 corresponds to negative positive 0.67. And to find they want to find the middle, the values which they lie between. So the lower value, we shall say, let's just say, so for this one, X will be Z theta plus mean. X will be negative 0.67 times 200,000 plus 1 million. And if we work this out, our X ends up being 865,200. If we do the same for Z2, our X2, which is X1, ends up being 1,104,800 shillings. So that means our 50% lies between 865,000 and 1,134,000 incomes. Let's go through this number, the last one, quickly. Let me go through it so that we can end this. Then I share with you the PDF and go through it on your own. Fertilizer, 75% of fertilizer effectiveness, 70% of plants respond. In 150 plants, approximate the probability that between 100 and 110 respond inclusive. Use normal approximation. So here, the number of trials N is 150. The number of the probability of success, which is pi, is 0.7. Probability of failure is 0.3, which is the same as 1 minus 0.7, 0.3. Our me is number of trials times probability of success. So 150 is probability of 2. And that should give us, I think, 0.7, sorry, not 2, it's 7, success 0. I think 0.1, 0.5, yeah. That's 0.0, 105 is the answer. Then sigma is square root n pi f, which is the same as square root of n pi is 105 times failure is 0.3. And our answer is approximately 5.612. And continuity correction for between 100 and 110 inclusive we'll use for between, so we'll move outside. So this will be 99.5. If we have our scale 100 to 110 inclusive, when I say inclusive, that means this has to be part of it. That means our outer limit has to be this side, outer parameter has to be here, and our outer parameter also has to be after 110. So in this case, before 100, if we remove 0.5, we remain with 99.5. And after 110, if we add 0.5, we remain with 110.5. And if we are to get our Z1, for this to be 99.5 minus our mean of 105 divided by 5.612. Then for this Z2, 110.5 minus 105 divided by 5.612. Here our Z1 will be equal to 0.980, and our Z2 will be equals, our Z1, this is negative because this is less. Our Z2 will be equals to positive 0.980. And if we want the probability of between negative 0.980 less than Z less than 0.90, we remember from the previous examples that we just subtract directly. So if we go to our table and find the probabilities, 0.180 will be probability of Z less than 0.980 minus probability of Z less than negative 0.980. This gives us, if we go to our table, it will give us 0.8365 minus 0.1635. Therefore, our final answer will be 0.6730. So, like always, here we're given X. We're given X, and they wanted us to find probability Z. Probability P. So, for Z, X to Z, we just standardize. Then Z to P, we use the table. All right, all the best. Thank you for attending today. Thank you for those who have made it to the end. So I'll be sharing this shortly. Make sure to go through it to